Thank you very much. I'm Koji from Osaka. It's very nice to see all of you, and thank you for joining my talk. I'd like to thank Ben and Fabian and all the organizers here for kind invitation. So my talk is not actually using any Calabiao. I'm sorry. However, I'd like to say that, for example, if I consider landscape, then what is the definition of landscape? One way is to say is that it's a theory space. However, you have to actually think about the landscape as the theory space which is outside of swampland. So what's the definition of swampland? Swampland means that you have some quantum field theory which cannot be coupled to quantum gravity. So we have to make sure that what is quantum gravity. The most efficient or a nice way to define quantum gravity is to use ADS-CFT. Although ADS-CFT is not proven, I would say that if you look at the original paper by Madasina, then he says that the quantum gravity can be defined by quantum field theory. And for quantum field theory, of course, we know much better. For example, QCD. We know really much about QCD. And some part of quantum field theories can define quantum gravity. But if you want to define quantum gravity in this way, then you know how to map quantum field theory and quantum gravity. But we are actually missing how to actually relate those two things. So that's the main and fundamental problem in ADS-CFT correspondence. So you know that the machine learning can solve inverse problems. And of course, if I start in ADS-CFT, if I start with gravity models, some string theory compactification, then it's kind of easy to get to quantum field theory from quantum gravity. Since what you need is to prepare for some black-brane solution and take a near horizon limit. On the other hand, you have a D-brane. So you know what is a quantum field theory, which is described by this quantum gravity. However, if you start with quantum field theory, such as QCD, then you don't know how to construct the gravity model itself. So this is a kind of inverse problem. And in particular, since we know a lot about QCD, so if we know what is a corresponding quantum gravity for QCD, that would be great. And so far, of course, there has been a lot of effort on this direction. Starting from probably in 2004 by Kaj and Kash about how to introducing flavor blend into ADS-CFT. Many holographic QCD models has been proposed. But unfortunately, most, and I think all of those models suffer from the single issue, which is this. So all of those models, of course, start from compactification of string theory, or in some so-called bottom-up models, you start with some definite five-dimensional model, which includes a gravity sector. So starting from this gravity sector, what we do is to compute some physical observables, and we name it just a prediction of the quantum gravity model. Then you compare those predictions with some experimental data coming from hadron experiments or lattice QCD numerical simulations, and you compare those with these ADS-CFT observables. Then if they match and they are well cooperated with each other, then you say that this model is a very good one. However, the issue is as follows. So you need to be genius to come up with some certain model which actually gives you a nice observable which can be matched with the experimental data. But I'm not a genius, so what I have to do? So one thing is if you can solve this inverse problem of generating this metric out of this certain experimental data, then you are sure that this model is a good one. Since at least for this chosen observable, it fits very nicely without any detailed prediction part. So in this talk, I'd like to demonstrate by choosing one experimental data, I construct one metric which corresponds to QCD, and then using this model, I compute other physical observable by using ADS-CFT dictionary, and then compare that with other experimental data, and whether this procedure is successful or not, is, of course, dependent on this matching, the final one. So as for the procedure, for example, I chose, this is just a demonstration of an example. I chose this one. So this is a numerical simulation data of quark mass versus chiral condensate. Okay. So you can change quark mass in numerical simulations. And of course, dependent on that, this chiral condensate, which is one of the most important observables in QCD, can change, right? And these different lines correspond to different temperature. So QCD, of course, has various interesting phenomena dependent on temperature. If you are in high temperature, then you are in the confinement phase, but at low temperature, it's in confining phase. So I chose this black one, which is just on a critical temperature. The reason is that in QCD, there is a nice phase transition between confinement and deconfinement. And however, the bad part about ADS-CFT is that it uses large N quantum field theories. So whatever you have phases, the distinction between those two phases is first order, right? But in realistic QCD, since you're working with NC equal to 3, it's not first order. It's a crossover. So this critical temperature line actually is a kind of a problematic part for ADS-CFT model building, since we are working with NC equals 3, which is not large N limit. So this is crossover. And I'm interested in what kind of metric should be learned by putting in experimental data which is not at large N, but with finite N. Okay, then I get some metric function which I'll show you later. Then I compute some other observable. And one of that is once a metric is given, then I can compute QQ bar potential. So quark and anti-quark potential. And this is the result. The horizontal axis is the QQ bar distance. This is a quark anti-quark potential. So there is a linear confinement behavior plus a Debye screening part. And this is very nice, since if you compare that with some numerical QCD simulation, then it shares precisely the same behavior as this one. So flat part, Debye screening, linear confinement, and coulombic behavior at very close QQ. And I have to emphasize that this kind of QQ bar potential has never been computed in ADS-CFT correspondence. Whether you're missing this part, or whether you're missing this part.
So the bottom right's lattice, are they experimental results also?
Yeah.
And it's a similar behavior?
Right, yeah. So the potential itself is actually not a physical observable. So you have to assume this kind of potential and put a point like quarks inside, then solve this Schrödinger problem. Then you actually compare that with your hadron spectrum and its decay width.
But it's consistent with the...
Yeah, it's consistent. Yeah, it's consistent.
So this right-hand side is a new part of the story? I remember that you had sort of the left-hand side in China, where in the meeting in June, where you were using, beautifully, experiment to determine the metric, and there was this question of whether you could then make an extra prediction.
That's right, that's right.
And so you did the right-hand side.
Yeah, exactly.
Bravo.
Thank you very much.
That's very
Thank you
cool.
very much. Yeah, in China, I talked about the same story, but I used some material data here to produce some metric, but I had no idea whether it's a nice one or not. Yeah. But here I use QCD data in which, of course, many people working on this figure, and then it seems that it has a consistent prediction with.
And this QQ bar potential is from your 1809 paper?
Yeah. So one more motivation I want to explain is discretized quantum graduate spacetime. So in ADS-CFT, as you may know, that these days it has a nice connection with quantum information, like ADS-MERA correspondence or quantum information toy model of ADS-CFT, which is called Happy Code. So ADS-CFT spacetime is discretized in this way. However, and also, if you look back the history of quantum gravity, then causal dynamical triangulation in late 90s has a discretization of spacetime with those simplex. And this kind of discretization is, of course, important in defining quantum gravity when you want to evaluate, for example, a rich scalar on a given space. But there are infinitely many ways to discretize quantum gravity spacetime, and why this MERA is working very well in the case of ADS-CFT, we never know. So I'd like to try a neural network and discretize this ADS space by a deep neural network. The reason is that in a neural network, you know that there is a theorem called universal approximation theorem, which states that once you have a deep enough neural network, then it can express any complicated nonlinear function. So once you have a fully connected neural network and train this so that it can reproduce some nice feature of this ADS geometry, which is the CFT data, then it should automatically give you a nice discretization of the spacetime, right? And if it turns out to be a MERA, like MERA or a happy code, then we are very happy about that, right? So I want to try that, but my talk is not really at that stage. But one of the motivations to discretize the spacetime by neural network is that. Okay, so yes? What? This one. This one is, in fact, the same as this one. So I just wanted to specify what kind of CFD data I want to put in for the boundary condition of this ADS. And this black line is this bluish one. Yeah. I'll show you how you can put the CFD data on this CFD, which is the boundary of ADS later. So in the first part, this is actually the same content as what I talked in China. So I formulate the ADS and deep learning neural network correspondence. Then I use that to train my metric so that it can reproduce the QCD data. So first, this is a one-page summary of what is ADS-CFT correspondence. Of course, in the bulk, you have a gravity theory, but it's difficult to treat. So I treat only the classical scalar theory in five-dimensional geometry, which looks like this. This eta is the ADS radial direction, and f of eta and g of eta, these are unknown functions. And these needs to be trained so that it can fit the QFT boundary data. So at ADS boundary, which is at eta is infinity, f and g should behave like exponential function with L, which is the ADS radius. And this ADS radius also needs to be trained so that it can reproduce the QCD data. On the other hand, the other side of this ADS geometry is black hole horizon, eta is 0, at which, in fact, this f of eta goes to 0 as eta squared, since this is a horizon. So the temporal component of the metric goes to 0. And g is a non-zero constant, which is positive. So these are boundary conditions which f and g need to satisfy. However, if these functions satisfy these constraints, then f and g could be arbitrary. Of course, if you impose Einstein equation or something, then f and g are completely determined. But I'm not interested in Einstein equation. I want to know what kind of metric emerges once I give only the QFT data. So how you get a QFT quantity out of this f and g is as follows. So for example, the response function, which is most important in any quantum field theory, the one-point function under the source j, is given as follows. So you solve the equation of motion of this phi for under f and g, this metric, and solve it to get two modes. So one mode is exponential of minus delta eta. The other is exponential minus delta plus eta. So these deltas are called the conformal dimensions of this operator O. And normalizable mode, which is subleading in this expression, is corresponding to the expectation value of this operator O. And the other non-normalizable mode is source J. So you have two modes. coefficients are J and O. Those are QFT quantities. So this is solved at ADS boundary. However, you need to have the complete solution in all eta space. Then this phi also needs to satisfy black hole horizon condition at eta equals to 0, which is simply this. So once you impose this condition, then this J and O are related with each other. So it gives you O as a function of J. So in our QCD example, this J is a quark mass, and O is the chiral condensate. So this is one page summary of ADS-CFT, and on the other hand, in China, I showed you this one-page summary of deep learning. And if you if you understand this slide, then it's almost obvious that you can make a map between deep learning neural network and ADS-CFT correspondence. So what is a neural network? So this is a figure of a neural network. So these are called layers. And there are many lines in between those probes. So for example, these 4 circles says that this is a 4-dimensional vector, and for each circle, this is called unit. You put some number here, so 4 numbers, and it's called the first layer vector xi. So I is 1, 2, 3, 4, and then you map from this layer to the second layer by a successive transformation of this linear map and nonlinear map. A linear map is just a multiplication of 4x4 matrix on this vector, and those are called weights. And for each component of this map Wx, you put this activation function, which is fixed nonlinear function, to get the second layer vector. And then you succeedingly repeat this procedure to get the final layer, and then you come up with some number, the final number, which is given by this linear map. So this is a typical deep learning neural network. And how do you train this network? So first you prepare many sets, the initial vector and the final number, and this is input plus output. So you have to prepare many sets of this. And then you train the network by adjusting these matrices, those are called weights, by lowering this so-called loss function, that is E. So definition of E is given by this. So this Fy blah 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 is the final output for a given X input, and then capital F is the expected final value. And this distance between those given expected final number and the final number produced by this neural network, if this is minimized, then you say that this machine is well trained. So now I'd like to map this neural network or ADS scalar field theory to this neural network. So how do I do that? Now, in fact, there are several works which can relate a kind of differential equations to a continuum limit of neural networks. So you can Google those papers, and then, for example, if you introduce skip connections, and that correspond to some differential equations, and blah, blah, blah. So here, this is a very intuitive way to relate equation of motion to a neural network. So this is a bulk equation of motion for the scalar field, phi, so potential term, kinetic term, and the curved metric h of beta is appearing as a coefficient of this delta eta phi term. So h is a combination of f and g as a kind of a volume form. So it's an unknown function. Then you discretize this equation and introduce a pi field, which is given by phi prime. So this is the definition of pi as a difference of phi eta plus delta eta and phi eta. So this just says that pi is a derivative of phi. And this equation is rephrased as this way. So if you go to this Hamilton form, then the equation of motion, which is second order, is now reduced to a first order. Then this is an evolution equation. So the neural network representation is simply following from this expression. For example, this is a linear weight part, and this is the nonlinear part. So it's a combination of linear and nonlinear. It's not a multiplicative. The reason is that I take delta eta to be very small. So as a result, weight multiplication and activation can be kind of separated and combined as a sum. So at any rate, you can reduce these equation of motion to a neural network representation. And these green lines are the weights which needs to be trained. Since h of eta, which is unknown function here, is appearing in the map from pi of eta to pi of eta plus delta eta. So it's hidden in these green weights. So in this way, it's almost straightforward to map the language of ADS-CFT scalar field equation into the neural network, and this is a correspondence dictionary. So let me summarize. So first, the emergent space of ADS-CFT corresponds to the depth of layers. So of course, you don't need to map this one to that, but my original motivation is to discretize this quantum gravity spacetime. So it's natural to divide this emergent space into the layers. The bulk gravity metric corresponds to one of the network weights. And of course, if you have more degrees of freedom in your scalar theory or tensor theory, then many more parts of the weights needs to be trained. But in my case, it's very simple. It's a scalar equation, the single scalar equation under unknown metric. So this metric function is encoded into a single part of this neural network. The nonlinear response in QFD data corresponds to the input data, since, as I said, this O and J are encoded into ADS boundary behavior of the scalar function, and it is phi and pi at the initial layer. So this data is put to this input data. On the other hand, this horizon boundary condition at the deep infrared of this geometry correspond to output data F. So whether this given initial condition satisfy this horizon boundary condition means that the input data is positive or negative. And finally, the interaction part. So in my case, I use the scalar field equation, and you can come up with any model, like phi4 model, phi6 model. But the coefficient of that phi4 potential is unfixed. So in this sense, the interaction corresponds to activation function, but this activation function also can be trained. So the coefficient of this interaction term is also trained. So usually in neural network, you don't train activation function. This is a fixed nonlinear function. However, you can also train this coefficient. And I can introduce this coefficient as a training variable in PyTorch or Chainer in your favorite implementation of. Yes,
so
please.
So activation function, the one that best reproduces the data on both sides? Is that what you're training?
Well, in fact, I have to fix the form of activation function since this is given by this potential term. So if I start with phi4, then I have a definite fixed activation function. Yeah, but in view of how well you can actually reproduce this data, of course, you can come up with some other form of the potential. Yeah.
And so your activation function has some functional parameters in it that actually come from the theory, but then you can train what the right values are.
Right. So this subject is called improved holographic QCD, in which you allow arbitrary form of potential. And people use this, for example, some polynomial times log of some polynomial. So those kind of potential has been tried. And then people try to fix the numbers in this potential, the complicated potential, to fit some physical observables QCD. But here I use only a phi4 potential. Yes, Ben?
Supervised learning in the back of your mind?
Yes. Yes.
So then the output data that you need to generate is essentially the boundary conditions at the horizon.
That's right.
So but that means that you need to know what kind of geometry or what kind of background.
Oh, yeah. In some sense, yeah, you are right. However, the point is that here, the black hole boundary condition is quite robust. So it doesn't actually depend on this detailed function. So any horizon should be behaving like this. And using this, you can show this boundary condition. And this boundary condition itself doesn't depend on F1G in the bulk. Yeah. So this actually, so this can be derived from this condition. So if you don't like this one, then you can work with so-called confining geometry, in which you don't impose black hole horizon, but you impose some normalizability condition for this scalar field phi at the infrared. Yeah, you can also use that. Okay, so if you're fine with this dictionary, then I go to section 2. Do you have any more questions? Okay, good. So let me show you how QCD can be learned by my machine. So first, this is the picture which I follow in this section 2. I first discretize and construct positive and negative data from this black line, and then get some metric, and then compute these things and compare with some other numerical simulations. So the procedure is just 3 steps. I use QCD data and let the network learn the metric, and then calculate other physical quantities. So what is the QCD data? So as I said, I chose this one. The reason is as follows. So first of all, what kind of O as a function of J we can get in QCD? So there are many condensate which has been measured in lattice QCD. For example, one of the most important is this psi-by-psi chiral condensate. However, there are others, like other pion condensate, and also gluon condensate. And those are very important for QCD. However, since I'm working on for scalar theory in the bulk, so this operator needs to be scalar. And this psi-by-psi is scalar. And also, the corresponding source needs to be well defined. For example, if you take the energy momentum tensor as a one-point function of QCD, then energy momentum tensor has a spin. So of course, energy momentum tensor is one of the most studied in QCD, since it gives you energy density and pressure. So it's important for phase diagram of QCD. However, if you use that, then for the horizontal axis, you need to take metric. So background metric of QCD. And nobody has worked a numerical simulation of QCD in curved space. So that data is not available. On the other hand, for QQ bar condensate, the corresponding source is quark mass. Since in QCD Lagrangian, you have quark mass times psi-by-psi, right? So if you treat this psi-by-psi as an operator, then through the ADS-CFT language, the source function is quark mass. And then people actually try to change the quark mass in many, many numerical simulations. So this is one of the nice things, which and the reason why I picked up this thing. So I asked my friend and Dr. Unger kindly gave us some unpublished work on how you can relate quark mass and chiral condensate very close to the critical temperature. So this is one of the nice data. But if you know some other data, then please just tell me. So I picked up this black one. The reason is that at this temperature, it's very close to the critical temperature, and it should be interesting. So I picked up this beta equals 3.33 data, which translates to the temperature of 196 MeV. And then this green line is that. And then since it seems that there is no error bar for this black line, but in fact there are error bars. For this numerical simulation, at this stage there is no error bar, but if you want to translate this beta value, this is a coupling constant, to the temperature, then you need to have some dictionary to translate this coupling constant to temperature. And there you need to use Wilson loop, and the error bar comes in there. So in fact, there is an error bar of kind of this size. So I could evaluate those error bars and put error bars to produce this positive data and negative data. So positive data means that it is centered along this black line, and this error bar is put for all of these 4 dots. And then I generate random points in this rectangular space. And then if it is close enough to this black line or green line in this figure, then I say that it's positive data. If it's far from that, then it's negative data. Okay.
Koji, based on the axes, it looks like at 0.025 you're off by a factor of 2. Or is there an error on the axes?
Oh, this one?
Well,
This
yeah,
one?
for instance, at 0.025 on the right here.
Oh, I'm sorry. Yeah, so this is, so the notation of our upside and their upside is different. Yeah, so it's the same. It's the same.
It's the same.
It's the same, yeah. So I chose a different notation for this definition of spinors. So that's why it's...
Got it. And if you mapped it to the other variables on the left-hand side, it'd be exactly the same.
Yeah. So this green line is the same as black line there. Yes, thanks. So I use this data, and then I need to map it to asymptotic scalar configuration. And this is well known by 1998 paper by Klebanov and Witten. And of course, this has been used by many people who worked on holographic QCD bottom-up approach. So one has to be careful about this correction term. So I'll explain the importance of this. So first, there are 2 modes, as I said. So this is normalizable and non-normalizable and normalizable part. The conformal dimension of Q bar Q is 3. So I have to count the conformal dimension of this Q bar Q at UV infinity, since it should correspond to asymptotic ADS. So Q is 3 halves, so Q bar Q is 3. So this means that the number which should appear here is 3. And this is 4 minus 3, so it's 1. So minus eta, minus 3 eta. And the coefficient of these Q bar Q 1-point function and quark mass. And also the NC dependence, the numerical coefficient of these guys are quite important for the numerical simulations here. Thanks. And this can be fixed by considering the 2-point function of this chiral condensate operator. And it has been done by these people. And also, when the conformal dimension is integer, then you have to be careful that in phi-4 theory, there is a correction term which looks like this, where lambda is a coefficient of the phi-4 potential. So anyway, if you are careful enough, then you can compute this asymptotic dependence of this scalar field as a function of quark mass and 1-point function. And in this formula, I omit all the ADS radius dependence, which also needs to be trained. So now this is the neural network. So this is a prepared neural network for phi equation of motion. And the input value is mapped from quark mass and Q bar Q by this Klebanov-Witten decomposition. So I put the data here and then map it to phi input and pi input, then train these green parts. So here is the demonstration of the training. So on your right panel, this is the layer, so eta direction. So this side is ADS boundary, this side is a black hole horizon, and I have just 15-layer neural network. And these blue lines, this blue line is the initial condition, which is randomly generated, so it's zigzag. And then on your left panel, this is quark mass versus Q bar Q chiral condensate. And this thick part is the original positive data. But with this zigzag initial condition, all of data is judged as positive. So it's wrong. So I want to fit this original positive and negative by changing these weights, and weight correspond to the emergent space. So here is a movie. So let me. So gradually it tries to fit the data such that it has a nice overlap with these originally positive data and this fluctuating green ones. And the emergent metric looks like this. It goes down first, and then it goes up. So this is a trained data, a trained metric.
That's 10,000 equal.
What?
What? 10 times 999 equal.
So this is 10,000, yes. It's not 10 to the 1,000. It's 10,000.
So how long did it take, the 10,000?
It took like 1 hour or so to train. Yeah, it took 1 hour. Yeah. And here I also, yes, please.
Yeah, so what do you actually, so what's your cost function in some sense? What's your loss exactly?
The loss function, loss is it's a L1 norm, which is the distance between the original data and
Yeah, but so what are you comparing? Comparing the boundary condition?
Yes.
Because on your map this was essentially you wanted to have
right.
condition from phi.
Yes.
But that's not necessarily Q bar Q. Right?
So
That's on the CFT side.
The left is predicted given the learned metric, right?
right.
Yeah.
Right. So the loss function is the final value, as you say. Yes. And these green ones are judged to be positive by this one.
Yeah, but it's not. So what does it weigh? So is this essentially how far the left-hand side is off? Is this included as well in your loss function?
Right. Basically is that. But the exact form of the loss function is the difference between the given value of f, which is 0 at the black hole horizon, and the computed value of this capital F with this initial data by using this metric.
Sorry, so some Q bar Q loss is included in the training, or it's not?
What do you mean by Q bar Q loss?
Maybe I was confused, but so do you learn the metric and then use it to predict the left-hand side, or do you use error on the left-hand side to actually feed back into the network? Is that sort of what you're
Yeah,
saying?
so the question, like obviously with a certain background metric, I have produced a left-hand side picture. And so, but then, because the thing I'm confused about is where does the information about the middle layers matter? Yeah, if I'm just worrying about something at the boundary, you could have anything in the middle in principle. So where does this come in the loss material?
So the loss function which I used is one. I'm sorry, I come back to this one. So for this x, I chose this QCD data, right? Psi bar psi and MQ. And then these weights are trained. And then the loss is just the difference between this value and f. But in fact, since this evolution is the same as the scalar equation of motion, so final value of this Fy is in fact the value of this scalar field at the end of the neural network. And this needs to satisfy the black hole boundary condition if this is a positive data, right? And the real black hole boundary condition is 0. So the distance from 0 is loss function. So once it is trained, then these W's are determined. And that is a figure which I showed in the right panel. That's a metric.
And then you use that to predict QQ bar.
Yeah.
But
So,
would there be a way of knowing whether the metric is sort of correct in the middle of not at the either equals infinity and not at either equals 0, but somewhere in the middle? Would you have some way of knowing that what the network did is?
the network actually determined automatically. So this metric, these W's, if these W's have the form of this metric function, then it says that it gives you very close to 0 for positive data, and for negative data, it's very far from 0. Maybe.
We discuss that.
Okay, we can discuss that. Yes. So in this way, for this Q bar Q data, this one, I could train the neural network, and I read the weight, these are green ones, to determine the metric. And this metric is determined like this. And also the ADS radius is determined like this. And also the coupling constant in front of phi 4 potential is determined like this, yes. So using these, so this fixes completely the bulk model, which is reproducing the chiral condensate behavior exactly. And this metric, which is given by h, it's a derivative of log of volume function. And it is rephrased as f times g squared. This is exactly the volume as a function of eta. And this is the trained metric. And you see that there is a bump here. There is a bump here. And in fact, if you solve the Einstein equation, there is no bump. It goes straightly from this black hole horizon to ADS boundary like a monotonic function. But since I trained the metric such that it reproduces the QCD data, somehow it learns this bump behavior. I have never expected that. And my friend told me that there is the case of bump in quantum gravity. If you have an Einstein gravity plus quantum gravity correction, then the solution of black hole has sometimes this bump. So this one has been calculated for the zero black brane solution, which is quantum gravity corrected. So anyway, there is a bump behavior here. And then using this metric, by following the famous paper by Maldacena and Ray, Tyson, and E, since a metric is given, I could compute the Q-Cuba potential. For large distance, it is 0 because of this black hole horizon. But short distance, it is Coulombing because of this ADS boundary condition. However, in between these two, there is a linear potential part. And actually, this linear potential part is given from this bump. And I could compare this with lattice data, like this. So there are many lattice data, but all of them show that Coulombic plus linear confining plus device screening, like this. So somehow this trained metric which produce this linear confining part, in addition to the device screening part, seems to be quite consistent with the lattice QCD data. And I have to emphasize that in most of the, so in all of the holographic QCD literature, of course there is no such bump since people solved Einstein equation, and then it gives only a monotonic function, so there is no bump. That means that there is no linear confining part, and it does not reproduce the QCD numerical results. So here is the end of my story. So today, I wanted to report you how this trained metric which emerges in neural network can nicely produce a result which is consistent with QCD. Okay, thank you very much.
Thank you. Are there questions for Koji?